Hello students, welcome to my channel Engineering Education. Please subscribe my channel. Thank you.
In this lecture we are going to solve problem 11.6, chapter number 11, Rotodynamic machinery, from the book Applied Thermodynamics by Eastop and McConkey. Statement of problem 11.6 is: for the turbine of problem 11.5, the mass flow of steam for each set of nozzles is 4.5 kg per second. Calculate the length of arc occupied by the nozzles if the nozzle height is 25 mm and the wall thickness between them is negligible. If the blades of the wheel have a pitch of 25 mm and the blade tip thickness at exit is 0.5 mm, calculate the blade exit height for each row. So first of all, we will extract the given information in the statement. So from this statement, mass flow rate is given, that is 4.5 kg per second. Nozzle height is 25 mm, which is 0.025 meter. The pitch is 25 mm, 0.025 meter, and blade tip thickness at exit is 0.5 mm, which is 0.0005 meter. Also from problem 11.5, we have nozzle angle, that is 18 degree, blade angle for first row, that is 21 degree, blade angle for the second row, that is 35 degree, and that is the inlet angle for the absolute velocity for the second row is 26.5 degree. In other words, we can say that this is for first row, this is for fixed row, and this is for second row. These angles will be used in calculations. We have to find four things. First, we will find the length of arc represented by N, and blade exit height for each row. For first row it is L1, and for fixed row it is LF, and for second row it is L2. So we will find N, L1, LF and L2. So coming to the solution of this problem, so first of all we have enthalpy drop H1 minus H2 equal to CAI1 square by 2. This is taken from the nozzle study. So enthalpy drop is equal to CAI1 square by 2. CAI1 in the previous problem it was also given, which is 700 meter per second. So putting the values 700 square divided by 2, also converting into kilojoule per kilogram, so we will divide it by 1000. Simplifying this, we get the value which is 245 kilojoule per kilogram. So now to find H2, So the difference H1 minus H2, this is the enthalpy drop, is equal to 245 kilojoule per kilogram. So now to find H2 value from this, we can write that H1 minus 245. So from the previous problem, the value of H1 was 3214 kilojoule per kilogram. So simplifying this, we get 2969 kilojoule per kilogram. So this is the value of H2. Now at the exit of the nozzle, we have the value of enthalpy, that is 2969, and the value of pressure is 15 bar as mentioned in the previous problem 11.5. So at 15 bar and at H2 is equal to 2969 kilojoule per kilogram. If we check the state of the steam, so the steam is in superheated state. So going to superheated steam tables, at H is equal to 2969 kilojoule per kilogram and 15 bar. From the superheated steam tables, we will pick the value of specific volume, and that specific volume from the table V2 is equal to 0.159 cubic meter per kilogram. So this is the value of specific volume which we found from the superheated steam tables at 15 bar and 2969 kilojoule per kilogram. Now also at the nozzle outlet, the flow velocity is equal to CAI1 sin alpha I1. Now putting the values, CAI1 is 700 and alpha I1, which is the nozzle angle, 18 degree. So simplifying this, we get 216.3 meter per second. So this is the flow velocity. Now flow area. Flow area is simply calculated from the continuity equation. As we know that mass flow rate is equal to rho A V, where rho is the density, A is the cross sectional area, and V is the velocity. So replacing rho by specific volume, so we can write that AV by specific volume, or we are interested to find the flow area. So for this we can write like this: A is equal to m dot into specific volume divided by velocity, which is the flow velocity. This is the flow velocity represented by V. So now for flow area, putting the values, m dot is given in the problem, which is 4.5 kilogram per second, and the value of specific volume is 0.159 cubic meter per kilogram. Also the value of flow velocity is 216.3 meter per second. So simplifying this, the area comes out 0.003308 square meter. Also, we are interested in part 1 to find the value of N, that is the length of arc occupied by the nozzles. So this flow area is further equal to NL, where N is the length of the arc and L is the nozzle height, which is 25 millimeter. So from this it is further equal to 0.003308. So solving it for N, it will be equal to 0.003308 divided by L, and the value of L, which is the nozzle height, is 25 millimeter. So dividing it by 25 millimeter, also converting it into millimeter, so we can write this, we can multiply a factor of 10 raised to power 6 with this to calculate the value in millimeter. So the value of length of arc comes out from the calculation, N is equal to 132.3 millimeter. So this is the part 1 required, length of arc. Also to find the blade exit height for each row. So for each row of blades we have flow rate m dot into specific volume. This is actually the volume flow rate, volumetric flow rate, and it is equal to L CRE1 into P sine beta E minus T into N by P. This is the very general formula. Let's suppose this is formula is A. So if we are interested to find the blade exit height for first row, so this L will be replaced by L1. For fixed row it will be LF, and for second row it will be L2. So for calculating it for L1, the expression will become like this: L1 is equal to m dot into specific volume into P is the pitch divided by P sine beta E minus T into N into CRE1. So for we can write that this expression was written for first row. So now for first row we have written this. Now putting the values, L1 will be equal to the value of m dot is 4.5 kilogram per second. The value of specific volume is 0.159 kilogram per cubic meter per kilogram, and the value of pitch is 0.025 meter divided by, again P is 0.025 sine beta E, that is 21 degree. This is actually beta E1 for this specific case, minus T. T is 0.0005 meter, and the value of CRE1 is 530.2 from the previous problem, meter per second. So simplifying this, we will get the value of L1, which is 30.2 millimeter. So this is part 2. Now to find the fixed row blade exit height, for that again we will rewrite the equation A and will put the values accordingly. So for the fixed blades, this was for first row. Now for fixed blades, we can write that LF is equal to, I am directly putting the values, mass flow rate is 4.5 kilogram per second, and the value of specific volume is same, 0.159. The value of pitch is 0.025 meter, 0.025, and here we have change only in the angle. In this case for fixed rows we have 26.5 degree angle minus 0.0005. Also there is change in the velocity. CRE1 is replaced by CAI2, and the value of CAI2 is 380.1 from the previous problem. So simplifying this, the value of LF will come out 33.4 millimeter. So this is the value of LF as required in part 3. Now also to find the value of blade exit height for the second row, again rewriting equation A for this. So for second row, again L2 will be equal to, putting the values directly, for mass flow rate is 4.5, specific volume is 0.159, pitch is also same 0.025 meter, 0.025, only change occurs in angle and velocity. Here angle is, for second row it is 35 degree minus 0.0005 into the value of velocity, which is CRE2, and that is 251.7 from the previous problem. These values 251.7 CRE2, CAI2 and 530.2 is CRE1. These values have been calculated in the previous problem. So now simplifying this, the value of L2 is 38.9 millimeter. So this was required in part 4. So we found the value of N, the length of arc occupied by the nozzle, and the blade exit height for first row, then fixed, and then L2 is the blade exit height for the second row. So this was the required solution of problem 11.6.
Thanks for watching. Please like and comment on my videos. Also subscribe my channel to get new videos.